course, we're going to be looking at radio frequency spectrum, identify basic facts about the electromagnetic wave theory. Remember, you got to get 70% on the KPC. This is the AFSC application. The idea is you got to know it in order for you to set up decent and solid communications. We're going to be looking at the layers and the three major factors that the ionosphere has possibilities with that can affect your signal and how you set your antennas up as well as your radios. Has to do with the layers of the ionosphere, looking at reflection, refraction, and diffraction. So we're going to quickly go through it and highlight everything. Now, with layers, we are talking about two different types of spheres that affect our comm, and that's the tropo and the ionosphere. Now, the ionosphere propagates through like the exosphere, the thermosphere, the mesosphere, the stratosphere, the thermosphere, or troposphere, but it plays more havoc with your longer wavelengths. But when you start getting up into your higher wavelengths, then it becomes an issue of going right out or using a tropo. Just remember, two major lowers. Of course, this is a kind of a quasi thrown together slide. Again, the tropo is the lowest. You're going to hear something called tropo scatter or common scatter. Normally it's in that 11 miles high. It can vary because we have these transition places between these particular spheres. It's pretty much where everybody does their radio comm, ground waves, over the horizon with their tropo. But when you get into your ionosphere, that's where we are looking at that approximately the 2 megahertz all the way up to 30-ish. And it plays a huge factor in what we are looking at. Because normally when you go out to a deployable area, a deployable site, first thing you got to think about is setting up comm. Well, the first thing you do is pretty much set up your HF first so you can reach back to the base so you can talk each other through when you get your SATCOM. Once the SATCOM is up, everything's done. That's mainly how some of the temporary bases that we set up do. Now there are three major regions that we look at. You got the D and E layer, gives you a background. The F layer is where we like to do most of our long haul communications. Now, long haul has two different meanings. Long haul can also mean through SATCOM because it does carry a lot more than what HF does. But the moment that somebody knocks the satellite out of the air, you got to rely on HF and you got to understand a little bit about it. There are two layers in the ionosphere, the F1 and F2, when the sun comes up. At night, it becomes F1 layer, or just regular F layer. The idea here is as the sun comes up and starts hitting that layer, it excites the atoms in there and the layers start splitting up. During the night is the best time to make lower frequencies propagate well, and during the day, it's the higher frequencies. Now, when we're talking lower and higher, we're talking from that 2 to 15 megahertz. That would be used more for nighttime, and then from about 15 to 30 megahertz, you're looking more for the day. Not saying that the lower frequencies can work, you're just not going to go as far. So again, showing you this blown up version of what the layers look like and what the sun does to the ionosphere. Not so much for the tropo, but we do have some issues with the tropo when we talk temperature inversion. Now, we do have something called reflection. The key part here is this sentence right here. Come on. The law of reflection states the angle of incidence is equal to the angle of reflection. And I point to this little area here versus this little area here. Angle of incidence here versus angle of reflection here. There are two different things you got to worry about when we look at reflection. You got something called the maximum usable frequency. It is in your study guide workbook. Take a look at it and see what you can pull from it. If you got any questions from it, please ask. Just remember that that maximum usable frequency changes throughout the day and night. If you got too high of a frequency, it goes into space. Too low, gets absorbed. Refraction, if everybody has ever put a straw in a glass, this gives you an idea. When you look at that clear glass, your straw is going to look kind of bent. Same with looking at fish in a aquarium. You think you're going to be able to catch that fish, and it's off a couple inches when you look at it. Kind of crazy for those people that have aquariums, and you kind of judge it. Key part on this one, right here. Bending of a wave as it enters a medium of different density. In other words, when you're looking at this straw, you're looking on the outside and you're going through one, the glass, and two, the water. So you got two different densities before you actually see the straw. Big thing is this is how HF is propagated through space. They do more refraction than they do reflection. Diffraction, this is where we are using, let's just say you're in a building, you need to get around that doorway, and you're able to get cell phones, let's say in Jones Hall, because that is a big concrete structure. Well, all this goes through the openings in the doors and every place else, and it propagates inside, let's say, the classroom, and you're able to get the signal. This is how it does this. And of course, lower frequencies, meaning down on the lower end of the frequency spectrum, the higher frequency, you're going to be able to diffract less. What does that mean? The lower frequencies are being able to be bent around a doorway versus a higher frequency is going to have problems getting through that doorway. So we've quickly gone through layers, reflection, refraction, and diffraction.